In this video, we solve problem 11.3.506.xp from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to use a graphing utility, to find the magnitude and direction angles of the resultant force of F1 and F2 with initial point at the origin. Magnitude and terminal point of each vector are given. We're asked to round our answers to 4 decimal places. So we're given two forces, F1 and F2. We're told that they have magnitudes 30 pounds and 70 pounds respectively, and each of those starts at the origin and extends in the direction of these terminal points. This one has a terminal point at x equals 10, y equals 5, z equals 3, and this one has a terminal point at x equals 12, y equals 7, z equals -5. So basically what's happening is I'm going to draw a cartoon to help us visualize it. We're going to go about 10 units in the x direction, 5 units in the y direction, and 3 units in the z direction. Of course, this is not to scale. I'll draw a rectangular box. Basically, you just want to draw line segments that are parallel to your coordinate axes. Doesn't have to be perfect. You do the best you can. So we go 10 units in the x direction, 5 units in the y direction, 3 units in the z direction. And this force F1 lies on the line segment that starts at the origin and goes out to that corner. So F1 points in this direction, but it doesn't have the same length as that line segment, or the line segment has a certain length, but it's not the same, as the magnitude of that vector. So we want to keep that in mind. Meanwhile, there's another force. It's acting along a different line segment. We want to go 12 units in the x direction, 7 units in the y direction, and then -5 units in the z direction. So we want to go down 5 units. So I'm still drawing a rectangular box, but this is below the XY plane this time. And actually, because I cut my piece of paper, we're not going to be able to see the whole thing. I have to extend like this. So we go 12 units in the x direction, 12 units in the x direction, 7 units in the y direction, and down 5 units in the z direction. There's another force that's acting on this line segment. And this force has a magnitude of 70 pounds. So I've got 70 pounds going this way and 30 pounds going this way. And the question says, find the magnitude and direction angles of the resultant force of those two forces. Well, remember how this works. If you're trying to find the resultant force of two forces, it's pretty easy. The resultant force is just the sum of the forces. So I need to find the force F1, but not in this form. I need it in component form. And the force F2 in component form. And then if I want to add these forces together, I just add component by component, and that's going to give me F in component form. Now, we're asked to find the magnitude of F first, which is easy. Once we find the component forms of these guys, we can find the component form of this guy. And once we have the component form of this guy, we can just find its magnitude. You take the components, you square them and add them and take the square root, no big deal. Now to find these angles, well, we kind of have to understand what those angles are. So we're going to briefly go over direction angles in order to identify alpha, beta, and gamma, talk about exactly what they're asking for here. And then we'll talk about how to find them. So let's say you've got a vector v in 3-dimensional space, and it has components v1, v2, and v3. So if I wanted to sketch it, I would go v1 units in the x direction, v2 units in the y direction, and v3 units in the z direction. And again, we're going to draw a rectangular box to visualize know what's going on here. So the vector starts at the origin and goes to that location right there. Now the direction angles for this vector, oops, they're not direction alphas, they're direction angles. They're the angles that this vector makes with the x-axis, the y-axis, and the z-axis. So the angle that this vector makes with the x-axis, that's the angle between v and I hat, is called alpha. And the angle that this vector makes with the y-axis, or the angle between v and j hat, is called beta. And the angle that this vector makes with the z-axis it's the angle between v and k hat, that's called gamma. So those are the direction angles. That's what they are referring to when they have that alpha, beta, and gamma in the solution, or they have boxes for alpha, beta, and gamma in the solution. So they want you to find the three angles that force makes with the positive x-axis, the positive y-axis, and the positive z-axis. So what I'd like to do now is relate those angles to a vector v that has component form v1, v2, and v3. Now, if we look at the projection of v onto the x-axis, I think we can all tell that the part of v that is parallel to the positive x-axis is v1. I mean, just by definition, we can tell that the projection of v onto the x-axis is v1. But let's say we didn't know that, and I want to find the length of the projection of v onto I hat. Well, according to our formulas from earlier, the length of the projection of v onto I hat is v dotted with I hat divided by the magnitude of I hat. Well, the magnitude of I hat is 1. So we just get v dotted with I hat. That's the length of the projection of v onto I hat. And since v has components v1, v2, and v3, and I hat has component form 0, 1, or 1, 0, 0, when I take the dot product, I just get v1 times 1, which is v1, plus v2 times 0, plus v3 times 0, because that's how dot product works. You multiply and add, multiply and add, multiply and add, and we get v1. So the length of the projection of v onto I hat, which is giving us the part of v that's parallel to that x-axis, is just the dot product of v with I hat. We get v1. Now, this dot product of v with I hat can also be written a different way, because we know the geometric definition of the dot product. We can write it this way. The dot product of v with I hat is the length of the first vector times the length of the second vector times the cosine of the angle between them. If I'm labeling the angle between v and that projection, or between v and I hat, alpha, this is going to be the cosine of alpha. So I end up with v1 is equal to the length of v times the cosine of alpha. In the same way, if I look at the length of the projection of v onto j hat, we end up with v dotted with j hat divided by the length of j hat, which is 1. Now j hat is the vector with component form 0, 1, 0. When you take the dot product, you multiply and add, multiply and add, multiply and add. When we multiply these two guys, we get v2 times 1. We get v2. The other guys are gone. They're just 0. But again, I could compute it that way with the algebraic form of the dot product, or I could compute this with the geometric form of the dot product. So I would get the length of v times the length of j hat, which is 1, times the cosine of the angle between v and j hat, which I've decided to label beta. So v2 turns out to be the length of v times cosine of beta. And similarly, the projection of V onto K hat, if I just look at the length of that projection, it's V dotted with K hat divided by the length of K hat, which is 1. So we just end up with that dot product. And I think you can probably guess what the answer is going to be. If I take the dot product algebraically, I get 0 plus 0 plus V sub 3 times 1, which is V sub 3. Or if I use the geometric definition of dot product, the length of V times the length of K hat, which is 1 because it's a unit vector in the Z direction, times the cosine of the angle between them. If I label the angle between them gamma, I get this. So what does that mean? Well, it means if our vector V has component form V1, V2, V3, that can be rewritten as V sub 1, which is the length of V times cosine of alpha, times I hat, plus V sub 2, which is the length of V times cosine of beta, times J hat, plus V sub 3, which is the length of V times cosine of gamma. And if I take my vector V and I divide by its magnitude, so that's giving me the unit vector in the direction of V, I end up with cosine of alpha, cosine of beta, and cosine of gamma. So this is nice. It tells us that it's very easy to find the angles that any vector makes with the positive x-axis, the y-axis, and z-axis. All we have to do is find the unit vector in that direction. Then we're going to have 3 numbers right here. If we take the inverse cosine of this number, we'll get alpha. And if we take the inverse cosine of that number, we'll get beta. And if we take the inverse cosine of that one, we'll get gamma. So that's what we're going to do. When we're asked to find the direction angles of the resultant force, well, first we're going to find the resultant force by finding component form of F1 and F2 and adding these together. We get the force in component form. Then we find its magnitude by taking the components, squaring them, and adding them, and taking the square root. That goes right here. And then we can find the unit vector in that direction. So we'll take that force, we'll divide by its magnitude, and that's going to give us these guys, cosine of alpha, cosine of beta, and cosine of gamma. And then by taking the inverse cosine of each component, we'll find the corresponding alpha, beta, and gamma. Notice that WebAssign is asking for the magnitude in pounds, which makes sense because the 2 forces that they started with were given to us in pounds. And then they show us alpha, beta, and gamma, and they leave a space, and they have that little symbol there. That means they want their angles in degrees, not radians. So make sure your calculator is in degree mode before you write these answers in here. And notice we're also asked to round our answers to 4 decimal places. Okay. So again, let's look at this picture from earlier. I've got a force of 30 pounds acting in this direction, a force of 70 pounds acting in this direction, and I want to know what is the sum of those 2 forces, what is its magnitude, and what are the direction angles associated with that. Okay, so in order to start this whole process, first I need to find the component form of F1. Now I know that F1 has a magnitude of 30 pounds, and it points in this direction. So if I call this location the origin O, and I call this point A, I know that my force points in the same direction as OA, but they don't have the same magnitude. The way I tend to think of this is I think of OA as being like a cable or a wire or something like that. And what we have is 30 pounds of force, like in that wire or in that cable. We know what the tension is in that cable, but we don't know what the direction is. Well, we know it has the same direction as this. So if I want to find this force F1, first I need to find the vector from O to A, and then I need to divide it by its magnitude. And the reason I need to divide it by its magnitude is whatever the length is of that cable, it's not necessarily the same as the magnitude of my vector here. It's like whenever you're playing tug of war or something like that. The length of the rope that you're pulling on is not the same as the force in the rope that you're pulling with. You can pull with 20 pounds of force on a very, very long rope, and the 20 pounds is not going to be the same as the length of the rope. I hope that makes sense. But the force and the rope itself, they have the same direction. That's the same thing that's happening here. So first I need to find the vector OA, because it's going to have the same direction as my force. Then I need to divide by its length, because I need it to only have a magnitude of 1. And then I want to rescale it. I want the corresponding magnitude, the magnitude for my force F1 to be 30. So I take the unit vector in that direction and I multiply by 30, and that's going to give me the right force. Now, the origin, of course, has coordinates 0, 0, 0, and A, that's my terminal point, has coordinates 10, 5, and positive 3. They gave that to us. I'll call that point A, and I'll call this point B. Well, I think we can see that the vector OA is comes from taking the coordinates of the terminal point and subtracting coordinates of the initial point. We're just subtracting 0 from everything. So this is just the vector with components 10, 5, and 3, which makes sense. We start at the origin. We go 10 units in the x direction, 5 units in the y direction, and up 3 units in the z direction. So that's our vector OA. And then we want to find its magnitude and divide by it. Remember, when you're finding the magnitude, you just take the components, you square them and add them and take the square root. So we get 100 plus 25 plus 9 is 134. So we're going to have 30 times this vector with components 10, 5, and 3, and we'll divide by the square root of 134. So we end up with 300 divided by the square root of 134, and then 150 divided by the square root of 134 is our y component, and 90 divided by the square root of 134 is our z component, and that's F1. F2 is very similar. If this is the point B with coordinates 12, 7, negative 5, well, F2, that force, has to have a magnitude that was given to it. It has to have a magnitude of 70 pounds. And it has the same direction as that vector OB. So we're going to take OB that points in the right direction. We're going to divide by its length to make it a unit vector in that direction. And then we're going to rescale it. We're going to multiply by 70 pounds. And then it's going to have the right magnitude, and it's going to point in the right direction to give us the force F2. Well, if the point B is 12, 7, negative 5, the vector OB, which comes from taking these guys and subtracting 0, 0, and 0, is just going to be the vector with components 12, 7, and negative 5. Then we'll take those guys and we will divide, or not divide, excuse me, we'll find the magnitude of the vector. So take 12 squared, 7 squared, and 5 squared. Add them, then take the square root. We've got 144 plus 49 plus 25. So that's the square root of 218. So I'll have 70 times this vector, all divided by the square root of 218. And that is 840 divided by the square root of 218, and 490 divided by the square root of 218, and negative 350 divided by the square root of 218. Okay. Now, if I want to find the resultant force, I need to take the two forces and add them together. It's actually pretty easy. If you've got two forces in component form, you just add component by component. So we're going to have 300 over the square root of 134 plus 840 over the square root of 218. So it's x component plus x component times I hat plus y component plus y component times j hat. Plus z component plus z component. Since one of the z components negative, we're subtracting. And that's times k hat. Now, if I want an exact answer, I can take each of these guys, square them and add them and take the square root, and then I can round from there. And that's going to give me as accurate an answer as possible for this little space right here. Or I can compute this and compute this and compute that and then round. I think I'm going to round, even though that means I'm going to carry some errors forward to avoid that issue. I'm just going to save more decimal places. So I'm asked for an answer with 4 decimal places of accuracy. I think I'll just go out to 6. So I have 82.808032 approximately. And that's also approximate. And then we'll do the last one. All right, so those are our components. We should take those, square them and add them and take the square root. And I get approximately 96.1265 when I round to 4 decimal places, which is what I was asked for, pounds. Now, when I move forward, when I compute the unit vector in this direction, so that I can find my direction cosines, I'd like to be slightly more accurate. So I'm just going to use more decimal places. Okay, so we're right here. And again, what we did was we found the component form of F1 and F2 by taking a unit vector in the direction of the force. So you find the vector that goes from its initial point to the terminal point and then divide by its magnitude to find a unit vector in that direction. And then multiply by the right magnitude. The magnitude of the line segment where the force is acting is not the same as the magnitude of the force itself. So that's why you've got to do this. You do that twice, and then you add them together. So you're adding F1 and F2 component by component to find F in component form. And then I took the magnitude of that, and this scalar is not equal to that vector. I can't believe I wrote that down. There we go. That's the magnitude, or in Calc 3 books, calculus books, you tend to see it with the double bars. With the single bars or the double bars, it's the same thing. After Calc 3, pretty much everybody does it with just the single bars. And we know from context that that's not absolute value, but that's the magnitude of a vector, since what's inside is a vector. And we get this. So we computed the magnitude of f because we were asked to, by squaring the components, adding them, and taking the square root. And now in order to find the direction cosines, we need to compute the unit vector in the direction of f. So you want to take f and divide by its magnitude to get the unit vector. Now I'm not going to write it down because there's a lot of digits here, but all I'm doing is taking this x value and dividing by the magnitude. So I'll do 82.808032 divided by 96.1264946, and that is approximately 0.86145. And we're going to do the same thing with the y component. So take the y component and divide by the magnitude. I know that you can store these numbers in your calculator. I've forgotten how to do that though, and I didn't care to look it up. But if you want to store this in your calculator, you could store it for x and then just divide these numbers by x. And that might make your computation a little bit simpler. Oops, I want negative 15.930175. No, 017. Yeah, 75. I typed 3, but I meant 5. So that's my z component, and I want to divide by the magnitude. And so I get that number. It's approximate. Now that's the unit vector in the direction of f. And the unit vector in the direction of f is by definition the vector with the direction cosines as its coordinates, or excuse me, as its components. So the cosine of alpha, where alpha is the angle that f makes with the x-axis, is equal to this number. Cosine of beta is that number. Cosine of gamma is that number. So if I want alpha, beta, and gamma, all I have to do is set this equal to this and solve for alpha by taking the inverse cosine of both sides. So alpha is the arc cosine of 0.86145. Or if you're looking at your calculator, it looks like a cosine to the -1. That means inverse cosine. I don't like that notation though because it doesn't look like, well, it looks like inverse cosine. It also looks like 1 over cosine, and that's not secant. So you need to be really careful. So that's our alpha, is the inverse cosine of this, or the arc cosine of that. Should have said this both times. This same thing. Beta is also an arc cosine. Gamma is also an arc cosine. And for beta, we're using this number. And for gamma, we're using that number. And these are just inverse cosine and an inverse cosine. Okay. So I'll use second. Now make sure your calculator is in degree mode, and if you're saying why degrees, why not radians? It's because that's what it said in WebAssign. They put a space and then they put a little degree symbol. That means they want the answer in degrees. And they asked you to round to 4 decimal places. So that first angle is approximately 30.5202 degrees. And the second angle is approximately 61.3117 degrees. And the last one is approximately 99 degrees. 99.5391 degrees. Okay, so what did we do? We computed the unit vector in the direction of f, and that gave us this. And then you compute the inverse cosine of each component of each of these numbers. To find alpha, beta, and gamma. So that's the plan. That's how we do that. All right, so briefly, let's recap. We're given two forces. We're given their magnitudes and their initial and terminal points. And we're asked for the resultant force and its direction angles. Well, in order to do that, first thing we needed to do was find the component forms of those forces that we started with. So you find the unit vector in the direction of the force, and you multiply by the right magnitude. So that way the resulting vector points in the right direction but has a magnitude of 30 pounds, which is what you want. If you just took this vector OA and multiplied by 30, it's going to be way too long. That's why you've got to divide by this first. This is not the vector OA. This is the vector OA, or divided by its length, which means it goes in the exact same direction, but it's 1 unit long. Then we multiply by 30 pounds, and then it's 30 pounds in magnitude. Same thing here. Find the unit vector in the direction of OB, multiply by 70 pounds, then it points in the right direction, and it has the right magnitude. So you find component forms of those guys, add component by component to get the resultant force F, and then compute the magnitude. Take the components, square them, add them, and take the square root. That gives you this. Then if we want direction angles, we need to compute the unit vector in the direction of F. So we take these three guys and we divide them by the magnitude, which is about 96 pounds. So we did this divided by this to get this number, this divided by this to get this number, and this divided by that to get this number. Now, by definition, those are the cosine of alpha, beta, and gamma because of this discussion that we did at the very beginning of the video. If you've got a vector, those components are the length of the vector times cosine of alpha, beta, and gamma respectively. When you divide by the length, you get the unit vector is given by this. So you get the unit vector in the direction of F. It's right here. And if you're trying to get alpha, beta, and gamma back, you take the inverse cosine of these three numbers to get those three angles. If there are degree symbols on WebAssign, make sure your calculator's in degree mode. Otherwise, assume you're in radians and switch to radian mode. So that's it. Please let me know if you have any questions about this one.